So aside from this property of the gradient, there is another important property and that is to say that the gradients are perpendicular to a level curve. Perpendicular to a level curve. So this is something that we can also prove easily, I think. And the way we're going to prove this is they're going to assume that we're going to be able to parameterize a level curve. So a level curve is, I don't know. Remember what level curves are? F of xy equals a constant. So you're letting z equal to that constant. You're essentially taking your surface and you're cutting it with a plane, a horizontal plane. And that's how we did those topography maps, is that they, whoever they were, they cut the mountains and all the terrain, they cut it with a horizontal plane, and then they traced out whatever's left and whatever they intersected, and that gives a specific height. And then they move up another 10 feet or so and make another cut. And then they keep doing that, and then you have level curves. So let's let f of xyz equals f of xy be a function. And just to be safe, let's call it a differentiable function. Because obviously we're going to take derivatives and we'll need to make sure that the derivatives are going to be okay. And then, so now what we're going to do is we're going to cut it. We're going to cut this, let's draw that surface since we're drawing it. So this is your surface, and then let's let k equal f of xy be a level curve. Okay. Now, what k should we choose? Well, I usually, when I draw that surface, I usually associate a point with it. So there's a point here, and the point, I usually look at the point in 2 dimensions as AB, but you can always put 0 in there, AB 0. But then if I look at it up on the surface, I have this point that's 3-dimensional, and that would be AB. What's the third component? Z, which is when you put AB into the function, right? So that's f of AB. Okay, so if we're focused on that particular point, what is the k, z is equal to k plane that we're going to cut it with? So I mentioned that there's this plane that's going to cut this surface at level k. So what is the height of my plane that's going to cut the surface if I want to include that point? F of AB, the z component of that point. So if I cut this plane that includes a z component of this point, then I would have made sure that I'm actually hitting that point. Okay. So now what I'm going to do is I'm going to parameterize that. And I'll parameterize that and call it R. So if I were to draw this R, how and where should I draw it? You understand my question? So I have a surface, I cut it, right? And then so I have an equation, K is equal to f of xy. F of xy is equal to a constant. So some relationship with x and y equal to a constant. Where should I draw that? This is a level curve after all, right? How do level curves look like? I mean, where is it drawn on, I guess is my question. No, what? On the what? No, not on the z-axis. It's the opposite of not on the z-axis. Oh, it's the opposite of z-axis. On the xy plane. On the xy plane. So this is just on the xy plane because there's no z's in it. Right? In fact, z was equal to f of xy, and then we took z out and let it equal to a constant. And by taking z out, this constant k, which is the same thing as the height of that surface, we cut it, and we don't look at it as a curve that's up in the air. We look at it flat on the xy plane. Again, the level curves that we see, your maps, your topography maps, are all kind of flat on the xy plane. Right? All you see are those curves on the xy plane. So I would draw this on just the xy plane without the z. And whatever that curve is going to look like, it's going to look whatever it's going to look like. But I know for sure that I have a point there, AB, on the xy plane. Okay, so this is the curve. I can call it z, or I'm sorry, I can call it k is equal to f of xy. But I've just parameterized it, so I'm going to call it r of t. And r, has an x of t and a y of t. Maybe I'll make that clear. Well, I'll just put it in the statement of the proof. Okay. So far we start off with a surface and a point on the surface. We cut it with a plane and found one particular level curve. And then we took that level curve and drew it on the xy plane, and then we parameterize it, r, x of t, y of t. Okay? So now let me ask you, about this composition f parentheses r of t. It's a composition of f and r of t. There's a few things we can say about this. What can we say about this? Any thoughts or comments about this? It's what? Anything? Think you might be able to say? No, not yet. We'll get there. So R of t is a curve in 2 dimensions. And then I want to, by saying f of r of t, I'm saying I'm going to put in all the values of r of t into the f function. Okay, so what do you think is going to happen when I put in those values into f? It'll be what? What plane? It's on the xy plane, but I'm going to put it into the function, which means it's going to be up there somewhere. So what can you say about when I put those values into the function? Well, it's a level curve, right? It's from a level. So if I draw this graph down here, it's just projecting any point on that graph onto the plane. And what can you say about the height, the y value or the z value of that? It's on the level. What level are we talking about? It's on the level k, the k level. Right? We cut it with a plane. We extracted the xy curve out of that. And then now we're going to put it back. It seems silly to put it back, but that's what we're going to do. We're going to put it back. So this move over here, if we take a look at that level curve on the xy plane, and we pick a point on the xy plane and then we put it into the f function, it's always going to be at the same level k. Okay? Is that exciting? No, it's not. All right, we'll see if we could actually do this for reals with an actual curve. But let's go ahead and finish this proof. This is in general. And so what I'm going to do now is I'm going to take the derivative of this thing. And notice that the derivative that I'm using is a straight d with respect to t, right? Because this is really a function of one variable. So it's just a derivative of one variable. But f is a function of two variables. So off to the side, you might want to say, oh, f is a function of x and y. And then x is a function of t, y is a function of t. So we got that special case of the chain rule that we've seen before. And if we want to take the derivative of that, you have to say f, the partial of f with respect to x times x prime of t, and the partial of f with respect to y times y prime of t. In fact, when did we start doing the chain rule? Oh, such a long time ago. '30th? October 3rd? Really? That's more cases. Let's see. When we first started doing the chain rule. Oh, first page. This is when we start doing the chain rule, when you first start doing the chain rule, right? And actually, from last lecture, when we kind of introduced the gradient, oh, it's not here. Never mind. Okay. So the derivative of this thing is going to be the partial with respect to x So we're also going to want to take the derivative of the right-hand side. What's the derivative of the right-hand side? It's constant, so that's just going to be 0, right? So what happens on the left-hand side? According to this table chart, it's going to be the partial of f with respect to x times x prime of t plus the partial of f with respect to y times y prime of t. Now, these are probably, should probably consider that they're being evaluated at some special points, but let's worry about that later. Anyways, from the chain rule, and we pull out the partial derivatives. And then we get this x prime and y prime. Is that fair? That looks like a dot product after all, right? What's the first vector? Right. First vector is actually the gradient, right? That's how the gradient's defined. So the gradient dotted r prime of t, and r prime of t would be some sort of tangent vector. Doesn't matter which way it's going, it'll be tangent to the curve. It says a dot product is equal to 0. What happens when dot products are equal to 0? They're perpendicular. So the gradient must be perpendicular to the tangent vector. And if the gradient's perpendicular to the tangent vector, then the gradient must be perpendicular to the level curve. Or perpendicular to the level curve. If it's perpendicular to the tangent vector, it must be perpendicular to the curve. Okay, that's it. That's the end of the proof. We've shown that gradients are not perpendicular to the level curve. Now, according to my picture, it looks like I have two ways to go. I drew two arrows for my gradients. And based on my drawing of the function, one of them is correct and the other one is not. Which one is the correct gradient? The one pointing inward or the one pointing outward? And you have to look at the surface to be able to tell. It's a 50-50 chance. Just yell out an answer, you'll 50% correct. What was the previous theorem before this? No, we haven't done acceleration. What's this say right here? Gradient's the direction of maximum increase, right? Now look at my surface and look at how I drew the surface, the level surface. Because that's the one going upward, right? So this is the correct gradient. Because if I look at the graph over here, it should be going towards the maximum. Okay. That makes sense? Well, the parameterization is just on the curve, and so whether your velocity vector is going one way or the other, it doesn't matter. The gradient is always going to be pointing in the fastest increase. In fact, this over here would also be an important piece of information. It's the negative of the gradient, and that would be the direction of the fastest decrease. Could play an important part for something. All right. Wow, that was a tough one. You want to see it with pictures or an actual example? Because we could see it with an actual example. It'd be nice. And is it okay if I use a simple example? No, use a hard one. Let's use a simple example. So let's use. Let me get everything set up. Let's use a simple example. Let's use a paraboloid, just going upward, or even going downward. I think we had a elliptic paraboloid with the guy that's going up or down, northeast or south or something like that. So let's do an upside down paraboloid. Z is equal to. Now let's do a right side up paraboloid. Let's just do a simple one: x squared plus y squared. Okay, that's my paraboloid. Let's pick a point. A two-dimensional point. 1, 2. So that's my point in 2 dimensions, right? Now let's pick what is the z value if I put 1, 2 into my function? Is it 3? 4, 5. 5? 5. Okay. So I have my point on the domain. I have my point that's actually on the surface. And now let's see what's next. Cutting plane. We need to cut it with a plane. What do we cut it with? Z is equal to whatever the z value we found, right? 5. And so I want to parameterize the curve. Z is equal to the function, right? F of x, y is equal to k. So that's my x squared plus y squared is equal to 5. So this is a circle, a radius square root of 5, right? So now I want to parameterize this. And we can parametrize circles, right? Circles is sine and cosine, or cosine and sine. I'm going to leave some space here because I'm going to make our radius to be whatever the radius is. What is the radius, by the way? So the radius is square root of 5. So if I put the square root of 5 into this function, or square root of 5 cosine theta and square root of 5 sine theta, I should get square root of 5 cosine theta squared. Oops. Okay. Slow it down. Square root of 5 cosine t squared plus square root of 5 sine t squared. This should equal to 5, I hope. Right? So 5 cosine squared and 5 sine squared, you pull the 5 out. sine squared plus cosine squared is equal to 1. So that's my height. Okay. So that's the setup, and the gradient is going to be what? Remember how to take the gradient? Just look at the function, take the derivative with respect to x. What's the derivative with respect to x? 2x. What's the derivative with respect to y? 2y. That's your gradient. Well, that's your gradient at some arbitrary point, but if we take the gradient specifically at 1, 2, we put 1 in for x, and we put 2 in for y, we're going to get what? 2, 4, right? So this is the direction of the gradient. Looks like it pointing outward. It's pointing outward. Okay? And it looks like it should be perpendicular to a level curve. So let's check that. R prime. To figure out the direction of the level curve, we need the tangent vector. So the derivative is going to be, the derivative of cosine is negative. So negative root 5 sine t, positive root 5 cosine t. We didn't talk about this, but what t value do I need to put in here so I can get 1, 2? Oh, that's not so easy. It's like cosine inverse of root 5 or something, 1 over root 5. I should have picked a nice point, like 1, 1. Inverse sine, inverse cosine, right? I guess inverse sine too. All right. So t equals arc cosine of 1 over root 5. Whatever that is. All right. So that's the idea. This is a simple computation of stuff. Let's actually see it with a graphing program. So let's put all the pieces of information here. So I have my point. Looks like I might have to zoom out a little bit. But this is my point down on the domain on the XY plane. And then if I were to figure out where my point is, it would be up here. Can't see it, so let's zoom out a little bit. There it goes right here. You see that point? That is directly above the point 1, 2 on the XY plane. And then we'll cut it with a plane. And we see that that point is actually on the plane, right? And then we'll get the level curve. to be the level curve on the ground. And if we take that level curve and project it up, then our z component is just going to be equal to 5. I don't know if you can see it. Let's take the plane out. See that curve up there? It's being projected up from the xy plane going up to this curve. Whoa, wait a minute. Okay. And so if we go back in 2 dimensions and find those tangent vectors, let's get that tangent vector on the xy plane. And for my vector, I'm going to keep my vector at 0 so that it's just flat on the xy plane. And then what was my gradient again? It's 2x, 2y, but then we put in values. What was it? 2, 2, 4. So this is still flat on the xy plane, and it's going in a direction that's going to increase. And if you're sitting on a bowl, inside of a bowl of a paraboloid, if you can, imagine the way you're going to get out to go up the highest is to go outward. Right? And so this is the outward climb that you need to make to go to the highest point. Does that make sense? And as you can see, it's perpendicular to the level curve. Okay? And we can draw the tangent vector, except we didn't really work that out correctly. But if we would have put the angle t is equal to, what is it, arc cosine of 1 over root 5 or something like that into the derivative function, then we would have our derivative, our tangent vectors there. Okay? All right, so these are the pieces of the components that help us show that the gradient is actually perpendicular to a level curve. So just a picture tour, so to speak. Okay, and you should be able to identify all the different pieces of this graph. And maybe I'll just draw out, since we didn't do the tangent curve. This is still flat on the xy plane. This is r prime of t, whatever t was. This is the gradient of f, evaluated at that r of t. And they're perpendicular to each other. Let me draw this. Trying to draw it parallel to the y-axis and parallel to the x-axis. This is r of t is flat on the xy plane. Okay. Any questions? All right. So, what are some of the ramifications? Well, ramifications, the word for it. What are some of the, I don't know. Oh, well. Oh, I know what. Let's go up a dimension. So in this scenario, if you have a function now of 3 variables, you have a function of 3 variables. Now remember, the fourth dimension is something that we can't see. So W, if we try to put all this together, W as a function of x, y, and z is not something that we can visualize. However, if we take a level surface by letting the function equal to a constant, so you would have a constant equal to some function with an x, a y, and a z in it. Now you're down to, from the fourth dimension, you're down to 3 dimensions. Just like our level curve goes from f of xy, and it goes down to just the xy plane. Your 4-dimensional surface, whatever this is going to look like in 4 dimensions, when you let w equal to a constant, it'll bring you back down to 3 dimensions. And now you have f of x, y, z, some relation with x and y and z in it, equal to a constant. That's a level surface. And that's something that we can view. Okay? And a gradient in 3 dimensions is just a 3-dimensional vector. And that 3-dimensional vector is going to be perpendicular to the surface k equals f of x, y, z. Okay, the proof is similar. You would parametrize a curve on the surface, and then you would compose them, and then you would take the derivative, and then you'll see that the dot product is going to equal to 0, except you're doing things in 3 dimensions. And, you know, technically you can do this in higher dimensions too, but then graphically we lose idea of perpendicularity, although you can study perpendicular 4-dimensional vectors in linear algebra. So, what does this mean? This means now if we have a funky surface, or a normal surface, a regular surface, like what does this surface look like? Okay, thought process, right? X squared, y squared, z, they're all squared, right? All of them are on one side. Are they all the same sign? No. So they're not all the same sign. So they're not a paraboloid because all of them are squared. They are not an ellipsoid because they don't all have the same sign. Hyperboloid. So it's just a hyperboloid. So, well, now is it a question of, is it 1 sheet or 2 sheets? It's 1 sheet because there's only one negative sign, or one sign that's negative, if you want to think about it that way. So, and so hyperboloids usually open up an axis. Which way is this opening up? The z-axis, right? Because that's the one with the different sign. All right, so that's the thought process. Now we have some idea what this thing looks like. I now want to find a point on this. Normally, when you do a problem, you'll have a point given to you. So can you guys work out an x, a y, and a z value that's going to be on this surface? 1, 1, 1 would work? Okay. That was easy. I thought it was going to be hard. Okay, so that works, right? When you put 1 in for x, 1 in for y, 1 in for z, it's going to equal to 1. So this is my point, and this is my function. Well, this is my surface. It's an implicit surface, but we can kind of step back and look at it as if it was a level surface from a four-dimensional function, right? So we can pretend that w is equal to a function of x, y, z, and that function of x, y, z is x squared plus y squared minus z squared. And then we're saying that this is equal to 1, which means it's a level curve. So f of x, y, z equal to 1 is a level curve, or level surface, I should say. And the surface is that hyperboloid that we just talked about. Okay? Does that make sense? So now let's take the gradient of this. And the gradient looks like it's going to be 2x, 2y, and negative 2z. So I have a three-dimensional gradient. And then that's just a vector. And if I take that vector and evaluate it at that point that I have, 1, 1, 1, I'm going to get positive 2, positive 2, negative 2. Nice, easy point. So now this vector should be perpendicular to this level surface at that point. We'll graph and draw it to see that this is actually true. So this time I'm going to find an implicit surface. I have x squared plus y squared minus z squared is equal to 1. Okay, as we expected, it's that hyperboloid of one sheet. Now let's make sure that that point is on the graph. I mean, it should be, right? Because we checked it. So that point is on the surface. And now we said that we had a vector whose initial point is that point on the surface. And what was our direction again? Was it 2? 2, 2, negative 2. That looks pretty perpendicular, right? Pretty cool. What can we do with perpendicular vectors? Make a plane out of it. Right? What? Huh? Yeah, plane. If I were to use this vector to make up a plane, what kind of plane am I going to get here? I'm going to get a plane tangent to the surface. Let's try it. Well, let's work it out first. What do I need for an equation of a plane? What? Two things I need. Point and normal, right? I have a point. I have a normal vector. I should be able to find an equation of a plane. So remember how to find an equation of a plane? I like to do it using x minus x naught, or some of you guys might like to do it with z's. I don't know. So there's two ways to do it. I'm going to do it by using the normal dotted with x minus x naught, y minus y naught. So I have 2, this 2, x minus 1, plus the next 2, x minus y minus 1, plus, oh, I have a negative 2, z minus 1 equal to 0. Some of you, I think, would prefer to just say 2x plus 2y minus 2z is equal to, and then the dot product, the d is a dot product of these two things. We'll get the same answer. In fact, I can even divide by 2, and then this whole thing would still be okay. All right? Anyways, I'm going to leave my plane like that, and I'm going to go ahead and check it out and see if it actually would match. Since I didn't solve for z, this is going to have to be described as an implicit surface. And I think I said 2 times x minus 1 plus 2 times y minus 1 minus 2 times z minus 1 equal to 0. Looking pretty tangent, huh? Okay. So with this, you can actually find a tangent plane. You can also find a normal line. That's another thing that they ask for sometimes. So let's find a normal line. What do you need for an equation of a line? Point and a direction. And since it's normal, we want the normal vector. So our direction is going to be 2, 2, minus 2. Right? I mean, we already have the vector there, so that's exactly what the line's going to look like. But let's draw it out anyways. So your line, equation for a line, since I'm kind of already used R of t somewhere, so let's use L of t, is equal to point plus t times the direction vector. And if I wanted to put this into the graphing program, I need to write it in parametric form. So that's going to be x is equal to 1 plus 2t, y is equal to 1 plus 2t, and z is equal to 1 minus 2t. Okay, so that's my function. If I let t go from 0 to 1, it's really going to be just that vector. If I let it go from 0 to 2, it'll be going in the same direction. And if I let it go negative, then I'll go backwards. So let's take a look at that. So this is going to be a space curve, 1 plus 2t, 1 plus 2t, and then 1 minus 2t. And this goes from negative 10 to 10, which is, I think, a lot. So let me start by going from 0 to 1. I don't know if you can see, but the vector kind of changed colors. That must mean that I'm redrawing that vector. If I make it go a little bit longer, then I went a little bit past it. Right? And right now it's not going backwards because I haven't defined it to be negative. But if I define this to be negative, I can start from negative 1. Then I'm going backwards as well. Okay, and usually when we talk about lines, we say infinite values of t, so it goes on forever. But this is going to be my graph. It has a tangent plane, it has a normal line. It all came from the gradient. So the gradient turned out to be a useful thing for us. Ooh. Yeah. Well, I'm figuring if nobody's asking, then nobody's looking. So, and I figured, oh, why should I post it? But yes, somebody had asked me about the videos also, which I'm still taking videos. I just haven't been posting them. Well, yeah, nobody's asked. Are you going to ask at the end of every week now? I just posted it this morning. And I'm going to do the videos starting backwards. So I've rendered a lot of the videos. I just have to upload them. And so I haven't done it. But I did a Monday and Tuesday's lecture videos are here. And Monday and Tuesday's lectures are here also. So all the notes are updated now. So the kinds of problems that you'll run into this class is finding directional derivatives, finding the direction of fastest increase, which we did, and I don't have any of those problems. But you have other problems that would be asking if you have a level surface to find a tangent plane and a normal line. So let me show you one more thing. This is gonna. So let's assume that you just have like a regular function. Oh, thanks. Let's assume that you have a regular function, z is equal to f of xy, right? And so this is a surface, right? If we bring the z over to the other side, we would get 0 is equal to f of xy minus z, right? Now this is a surface. Now we can think about this also as a level surface of a four-dimensional function. Because now you have a function of x and y and z, right? So we could say, oh, this is just some other function of x, y, z, and that's equal to little f of x, y, just two variables, minus just the third variable, z. And if you let that equal to a constant, then that's a level surface. Is that okay so far? This is exciting. Hold on. What's the gradient of capital F, that four-dimensional level surface? It's the derivative of the function, the newly made function, with respect to x and y and z, right? And it's the derivative of this function with respect to x. Now, this is just a variable z. There's no x's in there, so it's just f sub x, little f sub x, right? And if I take the derivative with respect to y, again, there's no y's anywhere else except for this function, f sub y. Now, if I take the derivative with respect to z, the f of xy has no z's in it. What's the derivative of f of xy with respect to z if it has no z's in it? 0, right? What do we have left? What's the derivative of this? What? What's your question? Where did the negative 1 come from? Well, last time we got negative 1, we got it by the cross product. This time we got the same normal vector. This is, by the way, it's perpendicular, right? So this is normal to the surface. And now we found the same normal vector, but now we found it using a higher dimension and treating it as if it was a level surface of a higher dimension. And then we got negative 1 again. Where did negative 1 come from? That was the question I wanted you to ask. All right, think about it. See you guys on Monday. We have school Monday, yeah? Yeah. Did you have to go to